Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is EET 121, Digital 1. Today we're going to have a discussion about fixed function integrated circuits and programmable logic devices. A fixed function integrated circuit is exactly as the name implies. The logic function is set by the manufacturer and you can't change it. A programmable logic device is a fully customizable logic device that you can tell it what you want it to do. Both a fixed function and a PLD come in something that kind of looks like what I've drawn here. Well, not drawn, presented to you here on the screen. It's basically a plastic case with a chip embedded inside it and pins radiating off the side. The pins basically carry your signals to the chip. And on that chip, it's a single chip with all your transistors, resistors, capacitors, etc. Anything you need is on that little tiny piece of silicon in there. And remember previously we discussed our nots and our ands and our ors. Yes, it's entirely possible to have a single not gate and a single and gate and a single or gate. Well, what they are is they are compressed and put all onto this one chip. Okay? The basic function of these things is, the basic reason of these guys is they're small size, high reliability, low cost, low power consumption. These things are basically mass produced in a semiconductor manufacturing facility, and once you've got a design, you can just crank them out by the hundreds, the thousands, okay? So they've been around for a long time, and they're going through various improvements, and they're just going to get more and more devices on chips as time goes on. So there's a number of ways to mount these devices. Even though, let's say for example, a counter, you have a counter integrated circuit. There are a number of ways to mount these things. The first thing that you're seeing right here, this one is a dual inline package, DIP. And it happens to be a through-hole mount. Because if you think about it, those pins are going through holes in a board. They're going to pierce through it. There's something else called surface mount technology. So that was through-hole mounting. There's also surface mount technology. And they're the same device. Let's say a counter with through-hole mounting and a counter with surface mount mounting. They're going to perform exactly the same thing, only one goes through holes, one mounts on a surface. No change in their function. The reason why we use the through-hole devices, they're easy to put inside a breadboard. A surface mount takes a little bit less manufacturing for the printed circuit board. And a printed circuit board, if you've ever seen it, it's that green fiberglass with copper traces on it used to connect your devices. A through hole would require holes drilled through there. A surface mount, oftentimes those devices sit in little cradles and they connect the pins. So our through holes, those are dual inline package DIP. The surface mount has a number of different profiles. Small outline integrated circuit is a very common one. If you look at a chip, it still has pins coming off of it, but they come out in this gull wing like pattern. And if you looked at it from the front, it would just look like a dip, slightly squashed. Okay. There are a number of different profiles. Yeah, I don't require you to memorize these things, but just look at them in your book. The LCC, that is a chip here. It doesn't have anything radiating off of it, but it does have these little spots on the side. And that is designed to be pressed inside a carrier. And inside the carrier are the connecting points. Again, it's a surface mount technology. You can just snap it in place. There is a really cool mounting technology. The fine pitch ball grid array, and that's also a surface mount. And what happens is on the underside of a chip, so we flipped it up out of its carrier. On the underside of the chip is fine pitch balls. So its mounting is not on the side, it's on the bottom. And it's designed to be snapped into a carrier where there are also connecting pins right there. Okay, so we are going to be using TTL through-hole dip. And we need to come up with a scheme to identify these pins. Okay, because there's a number of pins radiating off of it. And long story short, take your chip, find the identifier. There is a single identifier on it, whether it's a notch or a circle. Point it upwards. Go counterclockwise. Starting at 1, and let's say this one has 16 pins. 1 to 8, 9 to 16. Same thing with the LCCs. Even though there's no pins coming, this has pins radiating off it, by the way. Even though there's no pins on it, go for the identifier. What the identifier with those guys often is not a notch or a hole, it's a little bevel mark off to the side. Sometimes there's scribe lines. There could also be a dot on it. Okay, and if the dot identifier is right there, that's your pin 1. Go counterclockwise. Okay, so sometimes, but not always, but most of the time, these chips need to be powered. Customarily, your power and your ground for TTL chips. If you're looking at pin 1, here's our notch. And we're pointing it up, starting at the left and going counterclockwise. 1 to 8, 9 to 16. And again, this is customarily. Not all of them are like this, but get used to it now. You're going to see a lot of this. These are 2 important pins. Lower left, upper right. Lower left, customarily, is your ground. Upper right, customarily, goes to VCC. In our particular case, it's +5. That's the power supply. Not all of them are like this, but most of them are like this. So get used to it now. 1 through 7 are inputs for your logic circuits, inputs or outputs. 9 through 15 are also inputs and outputs for your logic circuits. Lower left and upper right, customarily reserved for ground and your power. Look inside the TTL Bible, which is basically a sheets of data sheets, and it shows you exactly the location of every single pin for the chip that you are interested in. Okay, so for our fixed function integrated circuits, there are levels of complexity, from the very simple to the super, super complex. And all you have to realize, I'm not asking you to memorize any numbers or anything like that, realize that there are levels of complexity. From SSI all the way up to ULSI. Okay, all these stand for small scale integration. Those are simply devices with 10 or 12 or less devices on it. Then you're going to step up to MSI, medium scale, large scale, very large scale integration, and finally you're at ultra large scale integration. So 100,000 plus gates. So when I was a student, ULSI was just coming out and I was often involved in VLSI production. But now ULSI, that is predominant complexity class for some of the devices that are being produced today. What we're dealing with for our digital 1 is oftentimes these 10 or less, or I think it's 12 or less gates on a single chip. Okay, there are different types of integrated circuit technologies. You've heard me already refer to in lecture is TTL, transistor to transistor logic. This is a type of logic device. Okay, what a TTL is, it's using +5 as our high, 0 as our low, and this is using bipolar junction devices. And this is something you're going to learn about in EET 221. There is something else called CMOS, and that is complementary metal oxide semiconductors. That is using MOSFET transistors. Again, you'll learn this in EET 221, what a MOSFET device is. Typically, this uses a voltage range of plus 3.3 volts to 0 volts. So typically less power consumption for a CMOS device. There's something called BiCMOS. As you can expect, it's a combination of these two guys where it's using bipolar junction transistors and MOSFET transistors. And now keep in mind for those individuals that are involved in PLC communications, all these logical devices that we're talking about here, TTL using 5 to 0, CMOS 3.3 to 0, think about the Allen Bradley PLCs that you're using. It's using a 24 volt high signal and a 0 volt low signal, very similar to some of the logic that we've already discussed. It just that happens that they're using a different logic levels, different voltage levels for the same logic device. Their AND gates and OR gates, even though they're instituted with contactors, very similar to the logics that we're discussing here. So Allen Bradley PLCs use plus 24 volts as a high. I also believe that Bachmann PLCs use 24 volts high for its logical high. So now we're going to go ahead and transition to a discussion of programmable logic devices. A programmable logic device, in contrast to a fixed function integrated circuit, is again, it's programmable. It's offering you more flexibility. And because you can program these things, summarizing a number of fixed function integrated circuits into a single programmable logic device, it's smaller. You know, another advantage of the programmable logic device is, remember our previous discussion about printed circuit boards, where you've got all these interconnections between a number of fixed function integrated circuits? Well, with a PLD, you're simplifying your printed circuit board in the fact that you have one device, which may require only a couple inputs and a couple outputs. You can change a PLD also, which is really nice about the flexibility feature of it, is say you've discovered an error in your logic that you're trying to implement, it can be easily changed. And in conjunction with changing, let's say for example, you have a existing manufacturing process and you want to upgrade, you can easily upgrade using the same PLD, programmable logic device. Let's say you need to add another input. If you've got enough pins, you can go ahead and add that another input. Another advantage of these things is they can actually implement a logic function faster. If you've got a single device, you can simply program it faster, less cost. Because again, time is money. Okay, so PLDs are divided into, I'm using programmable logic, I should actually say programmable logic with two M's, common spelling error. Programmable logic is divided up into technically two divisions. one of them being PLDs. The PLD is divided further into two divisions called SPLDs, simple programmable logic devices, and a CPLD, complex. What's the difference between them? CPLDs are more complex than a simple one. We'll get into the internal structures of the SPLD and CPLD much later in the course. I will say the SPLD will be divided up into further the PAL and the GAL architecture. A PAL is a programmable array logic. One time. It's like a hand grenade. You can only use it once. The GAL, you can reprogram it many times. So, what's more useful? Probably the GAL. How it uses it is how it creates these reprogrammable logic devices. It's simply a little fuse that it can be connected or reconnected, whereas the PAL, it's a fuse that once it's blown, and you can never get it back. Okay, so that's under PLDs, and then there's a final device, the FPGA. These are uber complex, field programmable gate array. It's still a programmable logic, but it's substantially more complex than any of the PLDs out there. One final discussion about programmable logic is the programming process. There's two ways of doing this. You can do it like on-site, or you might have to have a special apparatus. All this is saying is, let's say you've got a machine that just cranks out rubber ducks. And inside the rubber duck machine is a programmable logic device that's making all the decisions for this particular machine. Well, if you've got an on-site programmable device inside here, all you do is, okay, we want to change it to make rubber ducks with green eyes. All you do is you're going to hook up your laptop or computer with a cable, send the new logic instructions to the programmable logic device, and update it. And then you can disconnect and go on your merry way. Sometimes it requires special equipment. So that chip is going to be removed from the piece of the machine. It's going to put into a little programming device, which is hooked up to a computer. Then you're going to send the instructions. It's going to update the logic, and then all you do, put it back in. So if any of you have ever taken a programming language before, this may come to you as you've already understand this, but basically all these programmable logic devices which we just discussed require some programming. Okay, so this is not a course in C+ or BASIC or any of those other languages out there, but later on in the course we are going to be using a programming language that falls under the category hardware description language. HDL, hardware description language. One of the more common ones out there is VHDL, very high speed hardware definition language. And just like there's a number of the other languages out there, there's Verilog, HDL, and they're performing the same thing, but all you want to do is you want to program a device. They're just means of doing that. You can do some of the programs, the more advanced ones have graphic representations of an AND gate and a counter, and you just drag and drop it to a screen using almost something like a schematic and connect them together. Okay? The key thing that can be learned from any programming is you need to document yourself. As you go along, you're going to be writing these programs, and yes, it may be fresh in your memory now, but when you go back, and again, revisiting this, let's say that you were the guy that invented the original rubber duck program, you're going to forget what this specific logic function was supposed to do. So what you need to do is comment your programs and remind you, okay, this is designed to determine dimensions of such and such. Because when you come back 2 years from now to go ahead and reprogram this device to make your new customizable rubber duck with green eyes, you want to go ahead and, oh, okay, that's where I do the dimensions of such and such. So key thing is documenting your work when you're programming these. Another key step is basically testing the implementation. You don't want to just go ahead, write a program, burn it to your PLD, and just stick it inside the machine. That's not going to work, because guarantee there's going to be bugs or flaws, some mistake that you've made into it. So along with these things here, I'm going to talk about programming. I already talked about documenting your work with the use of comments, which are not included into the actual program, but they are comments for a user, for a person to read. Okay, we're talking about testing your design through a simulation. There is something called a compiler at the very end. Once you are very happy with your logical program, you're going to download it to the device, but the device is not going to recognize VHDL, Verilog, or AHDL. It needs to be compiled. And basically all that's doing is turning this very English-like language right here to machine language. Ones and zeros, blow this fuse, keep that fuse. Okay, so all it is just a means of translating English-like structures from our HDLs, our hardware definition language, to instructions that the machine uses to create the programmable logic.